At 21:58 on 6 July 1988, a pressure safety valve on the condensate injection pump system of the Piper Alpha platform was absent from its housing. It had been removed for scheduled maintenance and had not been reinstalled. A blind flange covered the open pipe end. That flange was not rated for operational pressure. The permit-to-work system that governed the maintenance cycle had not transmitted the status of the open condensate line to the incoming shift crew. The backup pump was available for activation. The grid was live. The Piper Alpha platform was a fixed steel jacket structure installed in the Piper oil field of the North Sea, approximately 193 kilometers northeast of Aberdeen, Scotland. The jacket was a lattice of tubular steel members driven into the seabed at a water depth of roughly 144 meters. The topside structures sat atop the jacket and contained 4 primary production modules designated A through D, arranged in a linear sequence. Module A processed oil. Module B contained oil and gas separation equipment. Module C housed the gas compression system, including the condensate injection pumps, responsible for re-injecting liquid hydrocarbons into the export pipeline. Module D served as the utilities and power generation center. The platform had a design production capacity of approximately 300,000 barrels of oil per day, though by 1988, output had declined significantly from peak levels. The gas compression system in Module C operated under high-pressure conditions, with condensate lines carrying hydrocarbon liquids under pressures exceeding 100 bar. The platform had been in continuous operation since 1976, and by 1988, its infrastructure reflected both its original design parameters and a series of incremental modifications that had been made over its operational lifespan. The physical arrangement of the modules meant that fire or structural failure in one zone had a direct mechanical and thermal pathway into adjacent zones. On 6 July 1988, condensate injection pump A was taken offline for maintenance. The maintenance task required the removal of a pressure safety valve from the pump system. That valve was extracted and sent to the instrument workshop for overhaul. In its place, a blind flange was fitted to the open pipe connection. A permit to work was issued for the maintenance activity. The permit recorded the valve as removed and the line as open at its connection point. The maintenance was not completed before the end of the day shift. The permit was left in a suspended state, meaning work had been paused, but the physical condition of the system remained unchanged. The pressure safety valve was absent and the blind flange remained in place on a high-pressure condensate line. During the shift handover from day crew to night crew, the status of the suspended permit was not communicated directly to the incoming supervisor. The permit was available in the control room, but it was not specifically reviewed or verbally transmitted as a live system constraint. The incoming night shift was therefore not operating with accurate situational awareness of the condensate system configuration. Condensate injection pump B, the backup unit, was in a functional standby state and was available for activation. The physical and informational preconditions for the subsequent event were fully established before the night shift assumed operational control of the platform. At approximately 21:45 on 6 July 1988, condensate injection pump A, which was still offline due to the maintenance activity, failed to meet production demand. Operating personnel on the night shift, unaware of the suspended permit and the open condensate line, initiated the startup sequence for condensate injection pump B, the designated backup unit. Pump B activated and began to build pressure within the condensate injection system. That pressurization propagated through the connected pipework and reached the blind flange that had been fitted in place of the removed pressure safety valve. The blind flange was not designed to contain operational line pressure. Under the load of approximately 100 bar, the flange connection failed. The failure mode was a sudden breach of the pipe end, releasing a volume of liquid condensate and associated hydrocarbon vapor directly into the enclosed environment of Module C. The released condensate under pressure immediately began to vaporize. The resulting hydrocarbon vapor cloud mixed with the air inside the module. The vapor concentration reached the lower flammable limit within seconds. An ignition source, the exact nature of which was not definitively identified in subsequent investigations, initiated combustion. The initial event was a flash fire within Module C. The time between pump activation and the first ignition event was estimated at approximately 2 minutes. The pressure excursion from the flash fire was the first of several sequential overpressure events that would propagate through the platform structure. The initial flash fire in Module C produced a thermal and pressure pulse that propagated outward through the module structure. The platform was equipped with an automatic fire deluge system, a network of seawater spray heads designed to activate upon detection of fire and to suppress flame propagation and cool structural steel. The system was capable of delivering a high-volume water flow across the affected module areas. However, at the time of the event, the fire deluge system on Piper Alpha was set to manual override. This operational state was standard practice on the platform. The deluge system had been placed in manual mode because the diving support vessel Pharos was conducting operations in proximity to the platform, and automatic activation of the deluge system posed a risk to divers in the water. Manual override required a human decision and a physical action to activate the system. In the immediate aftermath of the initial flash fire, the control room crew was assessing the situation. The automatic suppression that would have applied water to Module C in the first seconds of the fire did not occur. The fire was therefore not subject to any suppression action during its initial phase. The absence of deluge activation allowed the thermal event in Module C to continue without impediment. Heat output from the burning condensate increased. Structural steel surfaces in the module began to absorb thermal energy. The fire had a clear and unobstructed path to the gas riser pipework that ran along the exterior of the platform structure, connecting Piper Alpha to the adjacent production platforms Tartan and Claymore. The Piper Alpha platform was connected to 2 adjacent North Sea platforms by subsea and riser pipelines. The Tartan platform, operated by Texaco, was connected to Piper Alpha via a gas condensate riser. The Claymore platform, operated by Occidental, was similarly connected. These risers carried high-pressure hydrocarbon gas from the connected platforms into the Piper Alpha processing system. The risers ran up the exterior of the platform jacket and into the topsides modules. The operating pressure within these lines was high, sufficient to sustain continuous flow even in conditions of platform emergency. No automatic isolation or flow shutoff was triggered on the Tartan or Claymore platforms following the initial fire event on Piper Alpha, as neither platform received a confirmed emergency shutdown signal during the early phase of the incident. At approximately 2200, thermal degradation of the Tartan gas riser caused the line to rupture. The rupture released a large volume of high-pressure gas. The resulting gas explosion produced an overpressure event of substantially greater magnitude than the initial condensate flash fire. Estimates place the gas release rate from the Tartan riser at approximately 30 tons per second at the point of rupture. The Claymore riser subsequently failed under similar conditions. The combined gas input from both riser failures transformed the fire event from a contained module fire into a sustained high-volume hydrocarbon combustion event that enveloped the central and northern portions of the topside structure. Flame temperatures in the riser fire zone exceeded those producible by condensate alone by a significant margin. The Piper Alpha topside structure incorporated firewall barriers between the production modules. These barriers were constructed from steel-faced panels and were integrated into the module dividing walls. Their design specification addressed fire resistance. They were rated to contain the spread of flame and to provide thermal separation between adjacent process areas for a defined period. The specification under which they were constructed and certified did not require them to withstand the overpressure loads generated by a gas explosion. The distinction between fire resistance and blast resistance is a structural engineering parameter. A fire-rated barrier must prevent the passage of flame and resist thermal degradation for a specified duration. A blast-rated barrier must absorb or deflect a dynamic pressure wave without structural failure. These are different load cases, and the barriers on Piper Alpha were designed and certified for only one of them. When the Tartan riser gas explosion generated its overpressure pulse, the module firewalls received a dynamic load for which they had no design capacity. The barriers failed structurally. The failure mode was not thermal. The barriers did not burn through. They were displaced physically by the overpressure wave, transmitting the explosive load into adjacent module volumes. This failure propagated the pressure event laterally through the topside structure, exposing Module B and the pipe deck to direct flame contact. The collapse of the firewall integrity removed the last physical partition between the riser fire and the remainder of the platform structure. From this point, the event was no longer a localized process fire. It was a total platform engagement. The destruction sequence following the firewall failures eliminated the primary means of organized evacuation from the platform. Piper Alpha had two primary lifeboat stations, enclosed gravity-launched lifeboats mounted on davits at defined embarkation points. The structural damage and fire propagation from the Module C and riser fire events had, by the time personnel were attempting evacuation, rendered both primary lifeboat stations inaccessible or destroyed. The blast overpressure and fire exposure had compromised the structural deck sections beneath and adjacent to the lifeboat mounting points. Engagement of the lifeboat systems required access to deck areas that were no longer navigable. The emergency lighting system, which operated on dedicated circuits and battery backup, failed progressively as the fire consumed the cable runs and power distribution infrastructure. Sections of the platform that were not yet directly on fire were operating in conditions of partial or total darkness within minutes of the initial riser explosion. The radio communication grid experienced compound failure. The primary communication equipment was located in the control room, which was subjected to smoke infiltration and thermal loading early in the event sequence. Attempts to contact the Tartan and Claymore platforms by radio to request emergency shutdown and to transmit a distress signal were impeded by communication system degradation. Personnel were therefore operating without light, without radio communication, and without functional lifeboat access. The available option for survival was transfer to the sea surface via knotted ropes and hose lines from the lower decks, at a height of approximately 30 meters above sea level. The structural steel comprising the Piper Alpha jacket and topsides framework was standard structural grade carbon steel, consistent with the engineering specifications applicable to offshore construction in the late 1970s. Carbon steel in structural applications retains its load-bearing capacity within normal operating temperature ranges. As temperature increases, the yield strength of carbon steel begins to decline. The threshold at which structural steel exhibits significant strength reduction under sustained thermal load is approximately 400 to 500 degrees Celsius. At this temperature range, the modulus of elasticity decreases, the yield point drops, and the steel becomes susceptible to creep and plastic deformation under applied structural loads. At temperatures above 500 degrees Celsius, the load-bearing capacity of unprotected structural steel members declines rapidly. The riser fire, fueled by continuous gas input from the Tartan and Claymore lines, sustained flame temperatures well in excess of this threshold across the primary structural nodes of the topsides. The steel jacket members supporting the Module C and pipe deck regions absorbed thermal energy continuously over the duration of the fire. Passive fire protection had been applied to some structural members, but the volume and duration of the hydrocarbon fire exceeded the rated protection period of the applied coatings and boards. Structural members in the fire-affected zone began to deform under their own dead load and the load of the topsides. Lateral bracing members lost stiffness. Primary vertical columns experienced axial shortening under compressive thermal load. The geometry of the load path through the jacket changed as members deformed, transferring load to adjacent elements and accelerating their failure. The total mass of the Piper Alpha topside structure was approximately 14,000 tons. Following the progressive thermal degradation and structural failure of the steel jacket members supporting the topsides in the fire zone, the structure lost the capacity to maintain its geometric configuration under gravity load. The collapse of the topsides into the North Sea occurred in the early hours of 7 July 1988. The structural failure was not a simultaneous total collapse, but a progressive sequence in which the loss of individual members transferred load, caused further member failures, and produced a cascading geometric instability. The topsides descended into the sea in sections. The gas fires, fed by the Tartan and Claymore risers, continued to burn at the water surface and on floating debris following the topsides collapse. The thermal event at the sea surface continued for several days. The platform was a total loss. No structural element of the topsides remained above the waterline following the collapse sequence. The United Kingdom government commissioned a formal investigation into the Piper Alpha disaster under the direction of Lord William Douglas Cullen. The inquiry convened in November 1988 and ran for over 2 years, examining technical, operational, and regulatory dimensions of the event. The Cullen Report was published in November 1990 and ran to 2 volumes, comprising 106 specific recommendations. The inquiry established that the immediate causal sequence involved the permit-to-work failure, the blind flange overpressure, and the absence of automatic fire suppression. It further established that the regulatory framework governing offshore safety in the United Kingdom at the time of the disaster was prescriptive in character. It specified what equipment must be present and what procedures must be followed, but it did not require operators to demonstrate systematically that their platform, as an integrated system, was safe. Cullen's central structural recommendation was the replacement of the prescriptive regulatory model with a goal-setting framework built on the safety case concept. Under the resulting Offshore Installations Safety Case Regulations 1992, every offshore installation operating in United Kingdom waters was required to produce a formal safety case, a documented demonstration that all major hazards had been identified, that risks had been assessed and reduced to levels as low as reasonably practicable, and that a systematic management framework was in place. The safety case had to be accepted by the regulatory authority before the installation could operate. This constituted a complete architectural reset of the offshore regulatory system. The regulations entered into force in 1993 and have subsequently been revised and strengthened. The Cullen framework was adopted in modified form by multiple other offshore petroleum jurisdictions.